molecular stickiness that is the fundamental basis for chemistry, for organic chemistry, and certainly for biology and biochemistry. No offense, but you are an incredibly sophisticated pile of sticky molecules. I know. And you can even watch Netflix just by being a bunch of sticky molecules. It's fairly impressive. So let's look at what that means. The simple large charges plus minus attractions is called an ionic bond, which I put in bold. If he puts it in bold, he must have meant it. I mean, all of it, but I'm just trying to clarify. So we call these an electrostatic attraction. That means the attraction is based on large charge differences. Other things to remember when you're going to be doing your solubility lab, just like a large positive and negative charge will attract each other, if you have two charges of the same thing, two negatives or two positives, they will also push each other away. And we intend to use that property when we're separating molecules in the lab. So we're going to play on the natural charge tendencies of molecules. So ionic bonds are based on large positive and negative charges, not unlike the forces you might see if you were playing around with magnets for some reason. Covalent bonds are all about that word I have trouble saying. Electron. I have trouble with that second word there. Can anybody help me out? What's that word? Electron.
Sharing.
Sharing.
Sharing. Yes, I have trouble saying that word. I've always been an evil man. So really what you've got is two things adjacent to each other effectively sharing an electron. When you have, pay attention, a single bond between those two carbons, here's the little orbitals, those electrons overlap. They're basically sharing one electron worth of charge. If there's two bonds, try and guess how many electrons worth of charge they're sharing. Here's a hint. It's not one, it's not three. 0 and 4 are way out. If it's a double bond, they're sharing two. And if it's a triple bond, try to guess how many they're sharing.
Green.
Yeah, I know. And here's the problem. A whole lot of organic chemistry is so painfully obvious that it's almost impossible to forget. So if I jump too quick on stuff, tell me, we'll cover it up. So really we're looking at ionic bonds, great big positive and negatives that pull things together, sodium chloride, positive sodium, negative chloride, and situations where they share electrons. That's the single bond, double bond, triple bonds, 1, 2, and 3. We okay with that? How do you know I'm not making this up? Aha. I know, what a situation to be in. So the way we look at it, here's sodium chloride, a great big positive charge over the entity as a whole, and here's our chlorine, great big negative charge. There is lots of pull between a strong molecular positive and a strong molecular negative. Simple. Covalent bonds, though, here's those little orbitals, those electrons whipping around, they tend to overlap. And remember, electrons are actually whipping around so much that we only say theoretically they exist in a given spot because they're continuously moving at a crazy high speed. So here's H2O, water, thing they're mostly made of. Although in organic, I hear you're made of water and boredom. Here we have hydrogen sharing with the oxygen outer shell electrons, and that's a covalent bond. Overlap and share. You can do this, look, there, sharing. I guess I can say that word. We're okay? All right. Large differences, I mean, on a molecular level, of electron-activity, typically greater than a value of 1.7. You don't have to memorize that. I just threw it in as a reference. Almost always means there'll be ionic bonding as a first choice. The charges are so overwhelmingly strong and different, they're going to act like magnets and just ka-chunk, there they go. If it's what we call a small difference in electronegativity, in less than 1.7, it almost always forms a covalent bond. Now, we can cheat with that by using catalysts and using particular solvents that I'll talk about later. But in general, that's a pretty good rule. Now, the deal with carbon is its electronegativity is around 2.5. It is considered intermediate, and it usually isn't very different from other things around it. Because that difference isn't huge, it's going to be forming covalent bonds all day long. It wants to form covalent bonds with adjacent carbons. It wants to form it with hydrogens if they happen to be around. It needs 4 bonds, and it is absolutely content to form them with whoever happens to be nearby. Good enough? Polarity. Well, 2 things can happen when you're describing covalent bonds or when you're just talking about how a charge is distributed in a molecular entity. If the charges are all the same, it's not very polar. Now, if you've got a charge at one end of a molecule that's huge and one, that's positive and one at the other end that's negative, you've actually got 2 different charges in that molecule. That, just like a Winnipeg winter, is considered polar. So nonpolar is when atoms have a nearly equal charge attraction for electrons. So overall, somehow the charges are distributed. It's not asymmetrical, if you will. On the other hand, things like a free radical would have an unshared electron in this outer shell. Anything with that free electron is considered unstable and highly reactive. Ozone, O3 minus, anything with that big unresolved charge, it means business. So stable molecules, they have the correct number of electrons for their structure, whereas a free radical may have a missing electron or another charge discrepancy. So nonpolar, it's even. Polar, We describe the event of having one end of a molecule or atom as being charged and the other one charged a different way. We describe it by measuring what they're called dipole-dipole interactions. All that means is, how do the charges interact? What do they tend to do? And it's really easy. You get attractions between the opposite charges, and you get repulsions pushing away between similar charges. What that means, in addition to just, talking chemistry, is it means things that have this sort of polarity in them in a liquid are no longer going to float around randomly. In fact, they're going to tend to organize in a liquid because every one of the components has different charges in different places. And I'll talk about that a little more. People think water, yeah, it's fluid. You hold it up, it goes through your fingers. I agree. The reality is, though, you have a negative oxygen, which is negative relatively, and you have 2 relatively positive hydrogens. It's going to start to arrange itself in certain ways just in that cup of water you're about to drink. I'll demonstrate. That was me demonstrating drinking coffee. It really had nothing to do with the lecture, but I just thought I'd work that in there if that's okay. All right. Questions on this? It's all about the charges. It's whether they're the same charges. Are you sharing that charge? Or are there overlapping electrons? Are you sharing? There aren't really that many choices. It's not an infinite series of choices. So we use a little tiny letter. This is actually a sigma. Remember when you didn't take ancient languages in elementary school? This is what you would have not taken. This little tiny sigma means slightly. So the forces of attraction occur between oppositely charged ends of a polar molecule. For example, so here's our hydrochloric acid. Well, there's a pretty negative chlorine, slightly negative, and there's a slightly positive hydrogen. That means in a solution, and it's not going to float around randomly, the negative chlorine on the next guy is going to have a slight attraction to this proton, this slightly positive entity. Everybody assumes, liquids are just random molecules bobbing around. They might be. They also might not be, depending on the electrostatic makeup, depending on their charges. So slightly negative ends of something are going to be attracted to the slightly positive ends. Bigger charge, more attraction. If a charge is ginormous, it'll probably form ionic bonds, and that's a whole different story. We describe this event, the attraction between molecules in a liquid, as London forces. London forces basically is a huge long sentence that says non-polar molecules are attracted by relatively weak dipole-dipole interactions. For example, they could line up like that, which is strange, but more typically, they will line up positive, negative, end to end. And so there's a variety of different events based on the charges and how these things want to orient themselves, position themselves in a liquid. And we call that whole event of weird pushing away, pulling together forces. Those are all called van der Waal forces. Everybody thinks that liquid is sitting there inert. It is not. It is dynamic. The charges are causing things to attract, to push away. It is a very busy little area on a molecular level. Do any of you folks have like molecular vision? Dr. Henderson, are your glasses that good? Because I want a piece of those glasses if they could do that for you. Okay. So depending on what you've got, you'll have more or less charge. And, ready? The charges get weaker the further apart you are. If you pull magnets further apart, the charge gets weaker. That applies to all sorts of chemistry and biochemistry. The relative charge, even in the universal constant, begins to drop with distance between charged particles. Further apart, less interaction. That will also affect things in the big picture, like reactivity. You need to have enough stuff. You need to have enough stuff close together for any interactions to occur. So, although I'm only talking about charges, these very same things, molecular proximity, will be affecting whether or not things react. And I'll talk about that quite a bit later as well. Hydrogen bonding. This is so funny. It's one of the least, most unimportant, stupidest thing on the planet Earth, except for a number of points. Hydrogen bonds by themselves are incredibly small. Unfortunately, it's like somebody invited bikers to your barbecue. Suddenly, why are there 10 million bikers in the backyard? I don't like this anymore. They tend to show up in an environment that is protic or full of protons. And in fact, you get attraction between the very slight positive, for example, on this hydrogen, on a water molecule, ever so slightly attracted to this oxygen. And although it's a fluid liquid, and you're right there, I appreciate that idea, it is no longer entirely random. There is a certain amount of orientation, positioning, and physical shape orientation that is occurring, all because of this little, tiny, insignificant hydrogen bond. Other places they count. I will talk to you about this in the advanced biochemistry when I go over the genetic side and all the DNA and molecules. The entire backbone of the genetic code of your DNA, the double helix, is held together by little tiny hydrogen bonds across the sugar phosphate backbone. Millions and millions of them. The truth is, by themselves, they're very weak, but they tend to be in circumstances where there are many of them at a time. And again, I'm giving you a precursor to a talk we'll have a year from now. But these little guys don't do much, but actually, when there's lots of them, pretty strong as a collective unit. Just like you as students, by yourself, you're terrified, you're bored of my lecture, but as a group, you're still bored. Never mind. Bad example. Strike that example from the record, please. All right. Compounds that contain only carbon and hydrogen can't bond to anything. If all the bonding spots are filled, it's nonpolar, it's perfectly balanced, it's very content. Generally, it's not a very reactive molecule. That's why I was mentioning we always describe carbon compounds by the functional groups, by groups that are different, by groups that do have charges. And the trick is, when I get to it, not today, but when you go to name them, you name them for the most important part. And the carbon chain is never the most important part. So the functional group, the priority group, is almost always an area, ready, of greater electronegativity, greater electron density. It could be through oxygens, it could be through double or triple bonds. There's lots of ways. But one way or another, it's different from that long, inert carbon and hydrogen chain. Is that making sense? In any sense, Brooke, or are you just patiently putting up with me? A little of column A, a little of column B. Well, that's fine. In a very crude sense, hydrogen bonding acts as a generic low-level glue between different molecules. They're weak, but if you get thousands and thousands, you see, ready? Physical differences. Not just the chemistry. You're actually seeing phys-chem changes. For example, boiling points absolutely elevate when you start to get hydrogen bonding between things in a liquid. It can change the solubility. Things that can make hydrogen bonds with water, that is, interact with water, are way more soluble in water. They don't become water, but they are certainly perfectly willing to slide into it a lot better. Shapes of molecules. For example, the shapes of proteins. Proteins are described as having primary, secondary, tertiary, and quaternary structures. The three-dimensional shape is when hydrogen bonds in proteins begin to pull things together and ultimately make their three-dimensional shape. You know, it's just a stupid hydrogen bond, but that shape makes every enzyme work. And I'll talk about that later in biochemistry. Questions or thoughts? Lowly hydrogen bonds. Who knew? Alrighty. So, just to mention, I'm not going to go into the full naming here yet. I just wanted to sort of introduce the idea. Starting with alkanes, which is the carbon. How many bonds does it like? 1, 2, 3, 9, 4. Okay. You got 2 of them. It's an ethane group. And I'm going to go through all this, the naming in a bit. It's got 1, 2, 3, 4. What about this carbon? 1, 2, 3, 4. Okay. How about this guy? 1, 2, 3 carbons. Every carbon has 4 bonds. Here's the term you need to know. These are called saturated hydrocarbons. Listening in here, what are they saturated with? Ready? Hydrogens. These are saturated with hydrogens. Unsaturated would have a double bond, which means it isn't all hydrogens making that bonding requirement of 4. Take a look here. 1, 2, 3, 4. But if these hydrogens were missing, these carbons are still going to want to count to 4. And a double bond does that. We'll see that in a variety of ways. Dr. Manuel, is this making sense? I thought you were nodding off there, so I just figured I'd pick on you for a minute. All right. So whenever you look at any structure in organic chemistry, if there's a carbon, you know before you start, it needs to be attached to 4 things. If it is not, you need to pay attention to that spot. Somebody asked me about London forces. I'm just going to run back here for a second. London forces just describe the entire group of weak interactions by charge. That's all it is. It's not specifically this or specifically that. It's a whole family of very, very weak molecular interactions based on charge. And there's a whole range of them. I mean, we're not going to go into the entire course of that, but it's just a group of little tiny molecular forces that make things attract or push each other away. All right, now where was I here? So the simplest, most basic groups are called the alkanes. Alkanes are saturated hydrocarbons. You can have carbons, you count them up, that's going to be your name, and wherever you see a spot to put a hydrogen, you put them in. How many hydrogens go to a carbon? Anissa? 4. Yeah, yo. I don't even know what that stuff means. Those rap guys wave their hands like, what are they having, a stroke? I don't get it. I'd feel bad if they were asking for help and I just made fun of them. All right. So here's the naming prefixes that when I went over them the other day, you gave me this look. That was a pretty good look. I mean, it was pretty intense, but let's just go through these. If you have 1 carbon and 4 hydrogens, that's methane, period. If this thing is attached to something else, we call it a methyl group. 1 attached carbon group with hydrogens is a methyl group. What if it's twice as long? What if there's 2 carbons and 6? You go up here and count them. 1, 2, 3, 4, 5, 6. That is ethane. And if an ethane is attached to something, it's called an ethyl group. And I'd like you to notice, I didn't put these in for you to memorize. I'm sure you have more interesting things to do. But look, the melting point, by adding that extra carbon, it changes from minus 183 to minus 172. Check out the boiling point. It was at minus 162. Holy smokes, it's now at minus 8. It's almost doubled. It is shocking to me the change that you get in physical properties from very minor chemical differences. Propane, 3 carbons. 1, 2, 3, 4, 5, 6, 7, 8. Oh yeah, it is 8. 8 hydrogens is propane. Minus 187. It doubled again. Minus 42. We call a 3-carbon attached group a propyl group. I mean, you could say propane. Technically, I know what you're talking about, but usually they say propyl, and they put the YL at the end. But I mean, I'm going to go through all that naming stuff just to keep you honest. Right, pentane, 5 carbons. If you attach a 5-carbon group, it's called a pentyl group. If you live in the top floor of your apartment block, that is the pentyl house. It's as funny as I'm going to get. I'm teaching organic chemistry, for God's sakes. Hexane, C6, 6 carbons, is a hexyl group, also popular in covens. Octanes are for 8 carbons, octyl groups. Octopus. Oh, yeah. Do you mean these Latin prefixes show up all over languages? Why, yes, that's in fact, except for English. English is based on Latin, Arabic, French, and medieval Celtic. So it's really a mess. I'm apologizing for everyone who has to learn English. What a bad design. Ugh. Heptane is 7 carbons. Heptyl groups are attached. No name. Superstore sells no name products. 9 carbons. Nonyl. And decane is 10. This goes on. There's huge lists. I believe you could look them up without me running through an infinite number of names. Most of the stuff you're going to see is going to be down in the lower ends. Attached groups tend to be methyl, ethyl, etc. Are we okay with those? All these prefixes mean is how many carbons are in that piece that's attached to something. That's it. Methyl, ethyl, propyl, butyl, pentyl, hexyl, heptyl, octyl, nonyl. Whew, getting tired. I should give myself a raise. I only just recently found out a number of the other instructors are getting paid for this. I'm going to have to talk to somebody. So here's the catch. Even though you might have the same number of carbons, you might not have the same shape. And the reason I'm bringing this up is I know this is going to haunt you in instruments. Basically, you have 2 or more different molecules that have the same structural formula, a variation in the shape or the ordering. And so we use a prefix before the name out in front. We stick iso, not to be confused with the International Organization for Standardization. That's something else. In this case, iso means isomer of. And the really short cheater's version of this, it almost always means, ready? There's an extra methyl group, CH3, on the number 2 carbon. And the way they draw it, and I'll show you in a minute, it also implies that the total chain length is longer than the longest continuous chain. I'll have to show you that for that to make sense for you guys. So when it says iso something, it means there's an extra methyl group usually attached to the 2nd carbon. C4H10. What do we have here? I'm going to count these. Watch me do my counting. 1, 2, number after 2, whatever that is. I think it might be 3. Okay, well, I do have to deal with this guy. So you could go 1, 2, 2 methyl. So I'd say 2 methyl to identify that. And then I count this, 1, 2, 3. Okay, 2 methyl protein. But because it's on the number 2 carbon, you could also say it is isobutane. Observe the difference. When I used the iso, it now counts all of these things, even though they're not in a long chain, as being part of the molecule. So if somebody chucks the word iso in there, it doesn't mean it's attached and it's actually one longer, it's counting, iso counts everything. 1, 2, 3, 4 means it's butane, period. So 1, 2, 3, 4 butane, or you go, it's 1, 2, 3 methyl, methyl propyl, and that would be a 1, 2 methyl propane. I am completely content if you want to name things on a test either way. Not going to get judgy, just as long as I can draw the correct thing from what you write. 1, 2, 3, 4. This is in a row. There is no iso. It is methyl, methyl, propyl, butane. What's it called? It's called butane. That's it. So even though both of these have 1, 2, 3, 4 carbons, the physical shape is different. And your choices are to number it as a 2-methyl or to number it as a butane and use the word iso. You're not going to see this all the time. I'm going to tell you this because I think you're going to see, write this down, isopropanol sooner or later in your instruments class. Just saying, I could be wrong, but it's happened a lot in the past, so just be aware. And people are trying to figure it out and analyze it, and I go, did you ever think there might be a carbon hanging off in space there? Oh yeah. So just be aware of that, please. So the same molecular formula, but the shape is different, and because of it, their physical properties, the way they behave, are quite different. Butane boils at minus 0.5 Celsius, isobutane at minus 12 Celsius. It's a pretty significant difference for something with the same number of carbons and hydrogens. It's really all about the shape and the way that they're oriented. ISO, not International Organization for Standardization, but ISO for isomers of, is also used sometimes to name where the functional groups are. I won't do this a lot to you, but I just want you to be aware that sometimes weirdos, Andrew, you, would use ISO to describe the location of a functional group. I'd be just as happy if you numbered it, which is easier, I think. Just be aware of that. This is propanol. 1. How many carbons do we have here? 1, 2, 3. Methyl, ethyl, propyl. So I know it's a propane, except always, 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 we have to identify the functional group. Alcohol. You could legitimately say to me, propane alcohol, and I'd know what you meant. Most folks are too lazy to say that and to write it out. They'll just say propanol. So there's your propanol. So here's the difference. This structure is also 1, 2, 3. Methyl, ethyl, propyl. It is a propanol. It is a propanol with that functional group in a different position. In this case, the 2 is indicating the location of the hydroxyl group, functional group. I've also seen people go propane to all, which is an awful lot of work, but I've seen that done as well. But you do have to identify that this thing isn't sticking on the end. You could write propanol or 1-propanol. They mean this. That hydroxyl is on one of the ends. Period. The 2 means attached in the middle. Are we okay with that?
Can't we say isopropanol? Isopropanol? Because it's attached to the second?
Yeah, let me come to that in a bit, okay? I'm going to preface that with a little more. What I wanted to go over, and I noticed you guys weren't entirely as jolly as I'd hoped when I talked about it last time, is naming. Naming works like this. The root, the parent, the fundamental structure is based on, ready for this, the number of carbons. What's the root up here? 1, 2, 3. You're going to have to talk at some point, just saying. I can wait. I'm patient. Pay it either way.
30.
Green.
It is. So right away, when I look at things, I'm just instinctively, and this is the best way to be. First thing I do is I look, what's the business end of the molecule? I go like this. Oh, that's it. That's where it's going to react. That's how we're going to name it. I don't even think about it. I mean, it's, once you learn to read, you just read it. Alcohol. Then what's my job? Which one? Ethyl, ethylpropyl. Propyl alcohol, propanol. You need to get in the habit of what is the functional group, the priority group, or, what is that, the business end, and then count your carbons. And as I said in the first lecture, it is heartbreaking to see people not count to 2 or 3, which I'm telling you because I've strangely seen this happen a lot. So when I do these and I'm not sure, I literally write down on the structure 1, 2, 3. Can't go wrong with that. You're never going to miss. There is no point to miss. So prefix is only going to be there if there is a branch. Long flat chains aren't going to have a prefix. There's no prefix attached. So, here's something attached. Well, we're going to have a prefix, in this case 2, or up here, we're going to call it iso. Basic idea. Identify the parent by counting carbons. And again, I'm going to keep nagging this because I can't stand it. I feel sorry when people count wrong. What's the attached group, the important group? Is there a prefix? And what is your suffix? Is it an alcohol? It's OL. I'm going to give you a list of suffixes in a minute, and they're all quite obvious. So the particular rules are the parent compound is the longest continuous chain, ready, with the business end, with the priority group or functional group. The longest chain that you can draw or make that has that reactive center in it. You could even have longer chains. They don't count. It's the longest chain that has the reacting end, the functional end, or the priority group, all the same. You're going to have to number those side chains. They're going to be sticking on there somewhere. And in theory, try to number from the end that gives you small numbers. It doesn't always work. It just doesn't always work. And if you have the same group, like a methyl group a bunch of times, you name them like this. If there's 2 of something, we call it di. If there's 3 of something, we say tri. If there's 4, we say tetra, tetrahydrofolate. If there's 5, we say hepta. So diol would mean there's 2 alcohols or 2 hydroxyls on a molecule. That make any sense?
Just a quick question.
Sure.
So when you're doing like dimethyl or trimethyl, would you do with the numbers first? So where they branch off of? So like 1, 3,
Yeah, it's you're trying to keep them. The theory is you want to keep it alphabetical, so di before tri, and you want to keep the numbers low. It just always doesn't work. So although these are the rules, bear in mind that if you number them and I can count through them and it's all accurate, I'm good with that. No, I've seen people in the past, they go, oh, well, technically the rules in Switzerland. I go, what are you talking about? They're drawing the right thing. It's okay. So I'm not going to freak. But yes, you're 100% correct. So if it was 2 alcohols on carbon 2, I would say 2,2-dimethyl. So you said where they are, the number 2, and the di tells me, well, there's 2 of them in the first place. You just don't write down alcohol, alcohol. It would get really weird really, really quick. Eugene, I can see you'd like really weird really quick. Well, that's not going to happen. It's organic chemistry. Methane groups are methyl attachments. Ethyl groups, 2 carbons, are ethyl attachments. Propane groups are propyl attachments. It's that easy, folks. It's right off of that little chart, which I've lost. And, again, these giant guys, you're almost never going to see them. Where you will see them, I taught a course on natural health products, nutraceuticals, and pharmaceutics. And the most complicated structures by a country mile were some of the plant-based ones. I give examples out that are a paragraph long name of organic numbers and things. And the truth is, people just make up a new word to describe it because no human is ever going to name something 2,6,9 hexyl it gets crazy. So the chance of you coming across that, pretty small. Things you're going to see, expect to see, and know you're going to see, down here again, methyl, ethyl, and propyl. You'll see some butyl, you might even see a pentyl, but as they get bigger, it's less likely. So It's not a big ask. Methyl 1, ethyl 2, propyl 3, right? Even I could do it. I'm an idiot. I don't even work here. The real Dave died years ago. I just took his plaid shirt. No? The Dread Pirate Roberts. If you have simple side chains, and I think I'm starting, Bavik, to go towards your stuff here. What do we got here? So you know, I don't know if you've seen this diagram, just to refresh your memories. Sometimes in organic chemistry, they will not draw the carbons. They will not draw the hydrogens. If they do this type of line diagram, where this bend is a carbon, and automatically they assume the 2 hydrogens on it to make 4 bonds. They assume it. They don't feel like drawing it. Organic chemists get lazy. If you have to do this every day, it's a drag. They stop doing it. So what we have here is a carbon, another carbon. They don't draw the hydrogens. They assume you can count to 4. You guys can all count to 4, right? Thank God. Over here, we've got 3 bonds, so there must be a hydrogen as well. So let's count this up. 1, 2, 3, 4. Or 1, 2, 3, 4. Or 1, 2, 3, 4. Ethyl, ethyl, opal, wethyl. No, just kidding. It's butyl. There is no wethyl. I just like saying that because I see students' eyes get bulgy. So it is butane. You're going to have to identify the methyl group. To keep the numbers low, I mean, if I went from here, 1, 2, it'd be 3 methyl. You can make it lower. So to make it lower, you go 1, 2 methyl butane. You guys okay with that? Question. How do you know I'm not lying? No. It's like this asymmetrical power structure here. I'm not happy with that at all. I'm not. The prefixes, and this is where I wanted to get into sort of where those sort of add in there, Mr. Senpai. We have primary, secondary, and tertiary carbons. What does that mean? It's referring to how many other things, carbons, is something attached to. Soak that up. A secondary carbon is itself attached to other carbons. So a lot of people just write 2 with a degree sign, secondary, attached to 2 carbons. A tertiary or 3 carbon is attached to 3 other carbons. It's that simple. Here we have a carbon. How many bonds does carbon like? Still 4, huh? Well, you guys are stubborn. Okay, fine. Let me look. Okay, it's got 4 bonds. It's probably pretty stable. Now, do you guys know what an R group is? Perhaps you should try saying it with me. Imagine it's the 17th century. You're an Englishman drinking rum. You're in the Caribbean. You are pillaging. You would say R. That is the wrong kind of R. In this case, R means, ready? Write this down. An attached group that I was too lazy to write out or identify. But nobody says that. Usually it's an attached alkyl that is a carbon group. So if someone writes down R, it doesn't matter for what they're talking about or explaining that they go and name it. So they'll just call it an R group. Something over there is attached. And I'll go through this again a little more later. So you're going to get used to it. You're going to hear about R groups. It means something is attached there, not a hydrogen. We don't care what it is. I know. Who would have thought I could care so little? Gerline, did you know I cared so little? I know, it's amazing. So here, this carbon is happy. It's got 4 bonds. One of them is an R group. That's another, it could be a chain of carbons. It could be 1 carbon. Who cares? But it is attached to a different carbon and off down the line. What that says to me is it's bound to 1 other carbon. It's a primary carbon, 1 bond. This carbon has 2 hydrogens. They don't count. They're tiny and insignificant. This carbon is attached to 2 different carbons. We're calling them R groups. We don't care how long the chain is, but the fact that there's 2 other carbons or R groups attached means that this carbon is a secondary carbon. You guys following this? Because I'm seeing that sort of glazy look. I can't tell if it's the regular, what? Falling asleep, SpongeBob SquarePants trying to stay awake while this goes on, or if you're actually not getting it. Over here, tertiary. The head carbon is attached to 3 other carbons or 3 other main groups. 1, 2, 3. It is a tertiary carbon. Fourth bond made up by hydrogen. Finally, a quaternary carbon, draw the number 4, is attached to 4 other carbons or 4 other R groups. We don't care what they are. They're carbon-based. They're attached. That's it. R group, some other carbon-based thing attached, we're not going to bother to draw out. Very common to describe things in organic chemistry saying, for example, RCOH, formaldehyde. Nobody wants to draw it all out. They just get sick of it, honestly. Questions or thoughts? Attached to 1, attached to 2, attached to 3, attached to 4. Not attached to just 2 things or 1 thing, attached to 4 bonds, but 1 of them is carbon, 2 of them are carbons, 3 of them are carbons, 4 of them are carbons. Primary, secondary, tertiary, quaternary. Wow, I sound so mean for me. You guys okay with that? Just to keep nagging, if that group shows up a bunch of times in a row, the same substitute, it could be a bunch of methyls, it could be a bunch of propyls, don't care. If it shows up twice, you say dimethyl. If it shows up 4 times, you say tetramethyl. If it shows up 8 times and it's in the ocean, you say octopus. It's a very shy crowd. We're going to have to work on this. And there's more than one. Please put the number for the position. If it's on carbon 3, you need to write a 3 so we know where it is. That's all. Not hard. Position numbers, typically, according to the rules, you put a comma between them. For example, what do we have here? It is a line drawing. So they're not going to draw all the carbons. They're all sick of it already. They say this would be a carbon. They know that you count to 4, there's 2 hydrogens. Here's another carbon. You count to 4, there's 2 hydrogens. So let's count this. 1, 2, 3, 4, 5. Ethyl, ethyl, propyl, butyl. Penthouse, the apartment on top. It's got a nice balcony. You'd love that. I can't afford it. Yeah, so that's a pentane compound, except I want to deal with these 2. So I say it's clearly a dimethyl group. That's fine, yes. If you call this dimethyl pentane, you'd be half right. But it could be here or anywhere else. I need to know. So you would say 2, 2, because they're both on the same number 2 carbon, 2, 2, dimethyl pentane. You folks know what a 2,2 is? Nobody does ballet? None of you worked for the Bolshoi Ballet in Russia? Because I'd be really impressed. You'd be like the most killer athlete I've ever met. We try to keep these numbers as low as possible, right? 2s are smaller than 3s. And if you did it this way, 1, 2, 3, 4, you'd be saying 4, 4 dimethyl pentane. In a way, it doesn't matter. It's just as a force of habit, as almost an organic chemistry, courtesy. They always try to keep them smaller if possible. But again, I assure you, it's not always going to work that way. I'm not going to freak out, just as long as when you draw those words, you get the right structure. Guys okay with that? Is it truly horrible yet? I'm only warming up. Just wait. There's suffixes. There's a bunch. I wanted to pick some really uppity functional groups. Probably the one you're going to see the most common is oxygen. It's so common, I'm not putting it here. I have a whole separate piece for that later. Oxygen is an electron hog. It is all over the place. We call those carbonyl compounds. I'll get into that later. You tend to have nitro, as in TNT, nitroglycerin. Did you know when I was a boy, you could go to Farmer's Supply and literally ask the guy for a pound of blasting powder of TNT because Dad's got to blast some roots? Nowadays, they have much better laws, I have to say, because that was clearly insane that a kid could ride off on his bicycle like that. That's probably also why I became a chemist. Okay, fluorine or fluoride, things you might see, I don't know, in our drinking water. See what I did there? I tied the lab activity in there. Yeah, nice. Chlorine in that pool that you don't dare go into. It smells bad, and we had that talk about pools. Bromine, iodine or iodo. these are things you might see. They're obviously important functional groups. Why? They're great, strong negative charges. They are a reaction that is waiting to happen. We name things for functional groups because that's how the chemical functions. So the naming itself is based all about telling you what it's going to do, how it's going to function. So learning how to name is a real advantage because it's an alcohol. I know what's going to happen. I know where it's going to happen. I don't have to memorize anything. I can read it. You're much happier being able to read these. Trust me. Questions or thoughts, you guys? Suffering nicely? Stewing in your own juices? Nice. All right. You try as well, again, not always possible, to number those substituents, any of these other type functional groups, alphabetically if you can. And a lot of times you're going to find out I can't use the numbers in the alphabet the way I want. That's okay. Just telling you, that's perfectly fine. Sometimes you're not going to be able to do it. As long as it's accurate, no one's going to care. Little thing I wanted to point out, you folks are all like pretty athletic, right? You're all in like phenomenal physical shape, yeah? So if we were doing like extreme yoga right now on camera, you could reach behind your head and grab your own leg and bring it forward, right? You guys are in that kind of shape? If I don't ask to see it, are you in that kind of shape? You're so untrusting. Clever. Many compounds will do that extreme yoga and grab onto themselves. So instead of being a linear chain, they form a circle. Thus, we call those cyclic compounds. And so basically, it is a loop. When we draw them, we almost always just draw a line diagram because people are incredibly lazy. So here's a carbon at the corner. It's got bonds to other carbons. How many hydrogens would be on this carbon? Is it a billion?
Wouldn't be 2?
It would be 2. Sure. What about this one?
2.
Yeah. Remember,
2.
count to 4. That's not going to change, right? Carbon wants 4. Nitrogen wants 3. Oxygen wants 2. Hydrogen wants 1. That is the bread and butter of our business. It is that simple. So this is butane, 1, 2, 3, 4. They're fully convinced that you can count to 4 for some reason and are not making you draw those hydrogens. About this one, 1, 2, 3, 4, 5. I know what you're thinking. That is cyclo stop sign. Okay, I'm going to give you a technical pass. That's true. But it is also a hexane. 1, 2, 3, 4, 5 is hex. 1, 2, 3, 4, 5, 6. Oh, 6 hex, sorry. Brain damage. Cyclohexane. Hexane can be long in a row. Hexane can be short. Typically, they're usually 4 carbons long or longer. Because if you have short little legs, asking you to do extreme yoga, pulling your leg behind your head is really hard. So very short molecules obviously would have trouble folding over on themselves. Except I'll talk about examples later, just to be that guy. Questions or thoughts? This is hexane, cyclohexane, the loop. This is butane, 1, 2, 3, 4, cyclobutane. Easy peasy. So sometimes we don't have all the hydrogens. If a carbon structure has every bond filled with hydrogens, it is saturated, as I said, saturated with hydrogens. Sometimes it is not. And how many bonds does carbon want? I'm going to keep doing this. I am devoid of mercy. I can't even spell. I'm going to try to spell mercy. Wednesday, 7, clouds. No, can't spell mercy. How many bonds does carbon want?
4.
How many has this guy got?
4.
Yeah. 1, 2, 3, 4. If it cannot have 4 hydrogens, it will form a double bond to an adjacent carbon. That double bond is called an ene. E, ready for this? N, big finale, E, ene. And we call those not alkanes, which are just carbon single bonds, but alkenes. It is a structure, carbon and hydrogen, that has a double bond. What is a double bond, my friends? It is two of those orbitals overlapping. This position, with two of the orbitals overlapping, sharing electrons, is twice as electronegative as every single bond in the molecule. Ready? Listen close. Therefore, this double bond is more electronegative and probably going to have a reaction earlier than just regular saturated parts of the molecule. Any place you have greater electron density, whether it's a functional group like a hydroxyl or an oxygen or a chlorine, that's for sure negative. But when you have a double bond, it's twice as electronegative as a single bond. If you have 3 bonds between carbons, how much more electronegative is that going to be compared to a 1 bond?
Triple.
I'm asking a question just so I can drink coffee.
Triple.
Nothing to it. It is literally that painfully obvious. Ollie, is that making sense? How do you know I'm not lying? I could be lying the entire time. I could be, when I taught my sons when they were little kids the alphabet, instead of the letter D, I used the word pterodactyl. Their kindergarten teacher really gave it to me. Oh, well, it was a pretty cool time, though. All right, let's look over here. That's ethene. How am I counting it? 1, 2, methyl ethyl. Is it ethane? No, man. It's like reggae drums. Even a baby child feel that, read them. What we have here is a double bond making up for the missing hydrogen. That is it. That is all. Carbons need 4. They're just as content to form a double bond if no hydrogens are available. Down here, 1, 2, 3, methyl, ethyl, wethyl. Is it called wethyl, the third one? Wethyl? Is that it? It is? Don't let me lie to you.
Propyl.
Oh, it's propyl. Okay, good. Why did I start counting from this end? Good question.
The double bond.
The double bond,
Double
yes.
bond.
We always try to count from the functional end, and it's always going to be the same boring answer. Where is the electron density? Where is this different? Well, this is the only spot in this little molecule that is more electronegative, electrodense. Twice the electronegativity, that's our functional group. I mean, I get it. It's not as powerful a negative charge as chlorine, etc., but it is twice as much as the bond over here, period. So if something's going to attack it, that's the spot. 1, 2, 3. Propene. Why didn't I put a number in front of that, oh fellow scientists?
There's no functional group.
Oh, it's functional group right there.
It is
Because it's
first
equal.
Because
carbon.
it's on the first place.
Yes, it's equal in
It's
Why
equal
can't I,
to-
what if I started from here? 1, 2, 3.
because it's in the
Can't start from there.
I
But
think
it
you're
will not
answering
get
it right.
The lowest number then. The double
Well,
bond.
Truth is, this is the same structure facing either direction.
you need to name it.
You
with
drop
the
propene,
flower.
you're only going to get this. There's only 3 carbons. There's no other way to do it. If you drew it at this end, it's just the same compound, looking at it from the other side. There is no other variant here. Other thing I wanted to show you, you guys familiar with cis and trans? Oh, there's a whole movie called Trans Spotting. I went to see it. I got to be honest, I could not figure out the organic chemistry in that movie. It blew my mind though. All right. Cis and trans describes what's happening when you have a double bond. Lots of times, nothing. It's a chain. Sometimes, though, you're going to have a group attached on either side. I'll show you. Let me show you. I'm a double bond. Ready? If I have something attached, other than hydrogens, both on this side, it is called a cis, C-I-S molecule. If one of them is on the other side down here, that is trans. That was my train spotting joke. Never mind. Boy, you guys are bad at film. All right. So in this case, we would have drawn this like this. 1, 2, 3, 4. It's butane, methyl, ethyl, propyl, butane. And in the middle, we've got a double bond. But that means these methyl groups are attached. And here's the reason I'm telling you. These could be attached both on the same side of the bond. That is called cis. Or, just as legitimately, they could be attached above and below double bond. That is called trans. You're not likely to see it a ton, but you need to know that this is a possibility. Why do I tell you this? Because they can have different chemical properties. In every other regard, they're identical. But because of that change in shape, their ability to bond, their ability to react, can be fundamentally different. In pharmaceutics, we pay an awful lot of attention to little details like this for a lot of good reasons. We'll talk about that in metabolics a little later on. So if you have a double bond and there's stuff other than hydrogen, R groups attached, in this case methyl groups, if they're both on the same side of the double bond, it's called cis. If they're on the opposite sides, it's called trans. Isha, you good with that? How do you know I'm not lying? I know, I lie so often, it's almost impossible. Alkynes are when you have 3 bonds between the 2 carbons. The charge in here, with respect to electronegativity, is 3 times as strong as a single carbon-carbon bond. Therefore, it's 3 times more likely to be the site of reactions. It's considered a functional group. A functional group can be a large entity that has a charge, oxygen, chlorine, alcohols, etc. But it can also be inside the molecule as extra bonds. Those bonds mean extra electrons and thus extra electronegativity. So learning to read these really makes your life a lot easier. Also, the panic goes down. Ethine, 1, 2. It's an ethyl group, and we add the suffix -ine, Y-N-E. You don't say ethane, it's not ethane, it's ethine. There's the -ine. Here we go, 1, 2, 3. Propine, methyl ethyl propyl, propine. 4 carbons, butine,
Time.
pentine, hexine, red wine. You get the idea, right? Are you guys okay with that? You must have seen this at some stage of your academic career. Oh, grade 5 English? I don't know where they teach it now. It could be anywhere as far as I'm concerned. Okay. But just to make sure we're clear, the reason I'm going slow over this stuff is it makes it so much easier to do your naming, and you can get away with memorizing an awful lot less stuff, right? I'm not here to make you do useless work. I'd like you to work with ruthless efficiency and get the results. That's a much happier thing. I won't go too much longer. I want to make sure you have time to soak this up and actually get it, okay? Position numbers, when people write 2 and 3 and 4, and they're trying to describe the location of a double bond, it always assumes that the lower number is where the bond starts. So if you say 2, -ine, or 2-ene, it means the bond goes between 2 and 3. If you said 3-ene, the bond would be between carbons 3 and 4. And that is not magic. They simply agreed to that in the IUPAC nomenclature rule. IUPAC, International Union of Pure and Applied Chemistry, sort of like the naming police. Take a look. If you have 2 double bonds, what are you going to do? Well, here's 1, 2, ethene, 1, 2, 3, propene, 1, 2, 3, 4, butene. But look at this little troublemaker. There's 2 double bonds. This does happen because it's considered a functional group, right? There's a higher area of denser electronegativity. You've got to include both of those in the name. If you do not, you're wrong. So your job, when I look at it at least, I go, boom, a boom, 2 booms. I got to get them both in there. So I'm going to count them up. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Take your pick. 1, 2, 3, 4, 5. What do I have? 2, 4, pentadiene. Sure, that works. There's variations, I'd accept, but what are we doing? We're counting the number of carbons. There's 5. We're identifying there's 2 double bonds, di-ene, and then we're throwing numbers in to name them. Mr. Salazar, okay with this? You're chewing a lot of thumbnails there. I mean, you're gonna have to, maybe they grow at a huge rate. I don't know. Sometimes the prefix 1 is not even written down. I gotta be honest, organic chemists, once they figure this stuff all out, they get pretty lazy. And you don't write down 1 if you don't need to. It only applies in a circumstance when there is no other way to name it or to make it wrong. It just means it's got to be that way. Questions or thoughts so far, you guys? Are you able to go a little more? Are you able to withstand a little more of this horror? Look at you. You're like a deer in the headlights. Do I go left? Do I go right? What do I do? I don't know. You just stay there. Yeah, that's not good sound. A little more, a little less. Right? You were too weak to respond. I'm not going to get mad. It's just not going to happen, guys. But let's do a little more. Naming alcohols. Alcohols, the suffix is, ready? All. Is so patently obvious. So we, whatever the parent is, if it's methane, we say methan,
No.
all.
All.
If it's ethane with an alcohol, we say ethan, all.
All.
Is making sense? Absolutely nothing to it, folks. Methyl, ethyl, opal. We good with that? Even I could do that. Now, aldehydes and ketones is where it gets a little more interesting, not more difficult. These are 2 common things. They show up as sugars, as aldoses and ketoses in metabolic function. I'll talk about that a lot later. Yeah, they're very common. Every single aldehyde has this as a business end. Carbon double bound to an oxygen and 1 hydrogen. And then it's attached to something else. Who cares? We can just count those carbons. We're not even excited. A ketone always has 1 functional group and 2 R groups attached. Sort of a carbonyl group sandwich. So an aldehyde is RCOH, and a ketone is always RCOR. And I always say them as I'm channeling a 17-year-old surfer girl from Malibu, California. I don't know why, but that's how my organic chemistry brain works. RCOH, RCOR. Anhydrides, RCOO, COR. And in fact, people use these abbreviations because it's the easiest way to remember the structure and where the functional groups are. Yeah, I can use it for cheap laughs, but the reality is this is the single most common, most successful way people will go around naming these things. An aldehyde is always, always, always going to be RCOH. Ketones are always going to be RCOR. All of them, all of the time, no matter what. If something's an aldehyde, you end the name with, ready? Al. How hard is that? Too hard? Eugene, that's too hard? Come on, it's not too hard. This site here is the business end of a ridiculous number of organic chemistry reactions, not to mention biochemical reactions. Same thing here, a carbon and an oxygen. Because the oxygen is electronegative. It is always pulling electrons towards itself. That means this will always be a little more negative, and it means this carbon, carbonyl carbon, will always be a little more positive. I'll talk about that later. But just by knowing that this structure is there, you already know what's going to happen. Because this is negative, where would a positive thing attack this molecule? Right here. A positive thing attacks the negative oxygen. A negative thing, a nucleophile, will always attach the positive carbon. And I'll blow this up in detail a little bit. Methanol, 1 carbon, period. Methanol, 1, 2. Methane, ethanol, 1, 2, 3. Propane, propanol, count the carbons, add your buddy Al to the name. Do you guys have a friend named Al?
Yeah.
I literally have a friend named Al. He was the best man at my wedding. Over the Christmas holidays, he phoned me. He got COVID. He lives alone and he got it bad. He was very, very sick. So my wife and I were running over supplies of food, and the only thing I was giving him to eat was pancakes and pizzas. Do you know why I was giving a COVID patient pancakes and pizzas? Because it's the only thing I could slide underneath the door. Kidding. I gave him good food. I'm just kidding. Too soon? Okay, fine. You're a little sensitive. Ketones. You end it with a name. Ready? Own. Ketones can't be at the end of the chain because it's R-C-O-R. They're always at least one carbon in. You add the word own, and they will always, every time you do them, from now till then, you will have to have numbers. It will never, ever work out that you can name these without a number, except for acetone, but I'll talk about that later. Let's count our carbons. 1, 2, 3. Propane. Except I already can see the business end. This is R-C-O-R, ketone. So I'm going to say propanone or propanone. Let's count this one. 1, 2, 3, 4. What do we got there? Butane. Don't say butane. It's R-C-O-R. So I say butanone. How about this one? 1, 2, 3, 4, 5. Whoa. Dude, what's going on there? Blick, you're such a jerk. I know. Okay, take a look here. 1, 2, 3, 4, 5. Okay, so I know the main guy is pentane. So it's got to be a pentanone. Maybe I should deal with this guy. 1, 2, 3. 3-methyl. 3-methyl pentanone. Does that work for you? Okay, you know what? I could go on and I could literally do this till like 2 in the morning because I'm a complete psychopath. But I'm thinking, why don't you have the rest of your day? You can soak this up. Perhaps you will have some fine cheeses. I don't know. You guys don't like cheese? Seriously. Nobody likes cheese? Wow.
I love it. I love it.
Yeah, there's a stuff called Red Fox from Leicestershire, England. It is murderously good. Years ago, I brought some into the house, and my son picks up. He goes, "This is crumbly. What'd you get this old cheese for?" And he goes, "Dad, we have to have this every day, 3 times a day." And I go, "We can't afford that. Get serious." At any rate, soak up what we did. All of it counts. None of it's hard. Okay? Please, when you do have questions, ask me. I'll do my best to answer them. You know, if we have to back up and do it a different way, if we have to have a separate meeting and figure it out, we'll figure it out, okay? Our job is to count the carbons. How many carbons does, how many bonds does carbon like? 4, nitrogen, 3, oxygen, 2, hydrogen, 1. That is immutable. It is not going to change. So you don't have to guess how many bonds are there. It's science. It's already there. And as Beattini on Disenchantment would say, I believe it's pronounced science. That's not the way it's done. Don't call it science. All right, you guys. If you don't have other questions, I'm going to pull the pin on that. Have a good afternoon. I guess I won't be seeing you guys until, is it next week? You're not in my research group, are you? No, you're not. We're actually looking at the Omicron variant and miles of data. We're trying to do a meta study, epidemiology of the various stats we can get our hands on from around the world. I'm already believing that there's probably subvariants of Omicron with pretty similar virulence, but different morbidity factors. Again, there's just not enough correlated data to draw those conclusions as yet, but that's the kind of stuff we're working on. At any rate, that'll be me Friday afternoon. While you're off having your barbecue, or what do you guys normally do on Friday afternoons? Is it barbecues?
Work.
Study.
Did you say champagne? I was going to say studying organic chemistry. All right, you guys. I won't see you until next week. Have a charming weekend. Don't be afraid to do your resume and get a high-paying job. Just saying. I know you're a careers guy. He's a jerk. All right. See you later, folks. I'll talk to you on Monday or Tuesday.
Thank you.
Take care.
Thank you.
Thank you.